know me, I'm Ryan Glasser down at Tulane, and I have the pleasure of introducing the next two speakers who really need no introduction. The first of which is Professor Irina Novikova from the College of William and Mary, and she's going to talk to us about quantum shadows.
Thank you, Ryan. So first of all, thank you so much for inviting me here, and I'm completely humbled by being asked to present on this conference. John was a huge force in my life, and in reality, when I was sending my abstract, again, that's when you realize that you promised to send the abstract, and it was 2 days ago, and you really need to do something better, so you send kind of what you had. I think this is what it should have been. And when thinking about what I'm going to talk in this talk, I was trying to see how can I, talk about the science which John and I was working on, but also kind of give a tribute to John and his effect on my career. And I tried to strike a balance. I was trying to imitate John and trying to make it scientific and entertaining. So I'm sorry if it will be an extra example of how you miss John, because I'm not sure I can equal him. So the beginning is basically, I never quite figure out why John wanted to hang out with us. Because he's John Dowling. He basically tells presidents of countries what to do in terms of quantum world. Why he wanted to spend his time with a little girl from little colonial college, it's unclear. So my story here is that first you choose the occasions carefully. So I think the first time when really John kind of figured out my name is that on a day one conference when he was initiated as an APS fellow, and I happened to sit on his table, take some nice pictures of him. It's one of them, and then of course I emailed them to them. I think he felt good about it, and wanted to think, hey, can you come for the colloquium? So be in the right place, take the pictures. And I think that's after that, another thing, if you ever want to make sure that you have a lot of productive conversation, organize the conference on the boat, where the only thing you can do is listen to the talk and spend time in the bar, essentially. That was another, there were a wonderful series of conferences in boats in Russia organized by Olga Kocherovskaya. Obviously, we don't know what's going to happen with them in the future, but maybe somebody else will pick up the next transition. So after that, John and I start talking about things of trying to, what we can do together. And one of the ideas we start floating around is, can we do some quantum sensing, in particular quantum measurement? I just put this picture here, that's from my visit to Baton Rouge, 12 years ago. And mainly because some of the people who were students back then are in the audience, so they may enjoy seeing themselves. But that was a lot of fun, and I think that was more of the spirit of how these discussions were going back then. And then we like it, and we start writing proposals. And more proposals. More proposals. You got the joke. That's basically our mode of operation. I think most of the time we were writing some proposals, and maybe I finally can hear from Charles Clark why he never replied to any white papers we sent to him. It's still a mystery for me. But anyway, so and at this point we got really interested in the idea of the quantum magnetometry. So just because it will be kind of relevant to what I'm saying next, that was the basic idea. You have atoms. Atoms, like magnetic fields, their levels shifts when you apply magnetic fields. So when you shine the resonant light, it sees this effect of magnetic field in the atom by rotating its polarization. So essentially, because we have a long-lived coherence, so the magnetic field shifts the levels, and the refractive index of the polarization becomes different. Polarization rotates. You measure polarization, you know magnetic field. So this is the basis for a lot of magnetometers. Now, if you want to do something quantum, again, we don't have money. We're a small college. We don't have money for expensive crystals and powerful lasers. So we're using atoms again. So, but in this time, for example, if we send the linearly polarized light, in this case, instead of magnetic field moving the atoms, we have the Stark effect moving the atom, moving the levels. And we have basically a similar effect when the different circular polarization experience different refractive index. The polarization rotate, we call it self-rotation of elliptical polarization because the amount of rotation is proportional by how much ellipticity you put in. And what we're doing next is we're sending the linearly polarized light. And of course, in this case, it does shift the levels, but by the same amount. However, now we have to take into account the existence of the quantum noise in the orthogonal polarization. And that creates the cross-phase modulation between these two polarizations. So as a result, we have a squeezed vacuum generated in the orthogonal polarizations, and this is just one of the examples of that. So this is really kind of a poor man's squeezing because you don't need any expensive equipment to get one. You have your diode lasers, which we already have plenty. We have a vapor cell, and boom, you have squeezed vacuum generated. And that's actually the source of squeezed vacuum I'm going to mention in multiple occasions after that. So as I mentioned, our proposal writing was very exciting, but not super productive. So what do you do if you not get funded? You just do it anyway. So in this case, we did it by sharing the entangled student. So Ravi Singh, John had a lot of students who his mentors, and one of them, Ravi, wanted to do experiment. And John said, okay, great, go to Virginia and do the experiment. So, and that's exactly the experiments we did. And it was a lot of fun to actually work with John on something scientific. And we were able to demonstrate that you can enhance the performance. And just kind of one of the things which this work found is that the more atoms you have, the better performance happens until a certain point when this actually becomes not good. All right, so as I said, the proposal writing was continuing. So if any of you who are in the, especially the younger faculties, if you write your proposal, you get your rejection, just get used to it. It's just like how it is. But the nice thing about John, he never was really upset. Well, maybe once he was really upset. It was like, okay, great. Let's see what we can do on the next call. So it really taught me a lot in terms of how you approach it. But the funny story was that once we tried to contact different program managers, and we at this point Tatiana Kurshit was the FSR program manager, and we called her with our wonderful idea of a quantum magnetometer and said, yeah, no, what else can you do? I said, well, we have this question of we don't quite understand why things are not getting better if you have more atoms. And oh, that's interesting. Go work on that. And I can tell you at this point it was actually fun because basically John and I, got the good news, like, what are we doing now? Because it wasn't what we kind of have in mind. But the wonderful thing of working with John is we can always try something else. So this is basically our first generation of collaboration. Somehow I don't think we have a nice group picture. So it has to be this. And again, the Laguerre mode ended up playing a major role here, so I put them here as well. So as I said, one of the things we were trying to answer is that as we increase the number of atoms, all this simple theory which you find in the papers and textbooks is always have the factor of n in front of your nonlinearities or your effects, which means that the more atoms you have, everything should be better. Everything should be better, especially if you adjust the other parameters. And what we discovered that it's not. It doesn't really very important, but basically we're trying to optimize our squeezing. So you increase the power, which we can do, you increase the density, and it's very clear kind of the optimal conditions where it happens. And after that, things get worse. So, and nobody quite knew why it is so. We had a little bit of inkling of what may be happening is when we start kind of cutting the beam. If it's normal squeeze light, if you cut anything, you should reduce your squeezing. That's expected. However, what wasn't expected is it's really dependent on how you cut your squeezing. So for example, if you cut the edges, your noise your squeezing will disappear very quickly and actually becomes very non-squeezed. We have an extra noise. However, if you cut it in the center, it actually was behaving much similar to this. So that was a kind of inkling that something's happening on the scale. So what John at this point said like, well, maybe this is kind of a multimode. And I should say that again, that was very interesting. This was the first project which we had with John where we had to work, our groups worked together, kind of trying to solve the same issue, which none of us quite knew how to address. So I think the idea, the analog I can say, it was a very old jokes when they start building the tunnel under the La Manche, is that how long it's going to take. It will take 5 years if the two teams meet, and 10 years if they don't. So when we were starting this project, we didn't quite know if we actually going to meet it in the center. But we did, magically. I think it was a very nice surprise for everyone. I'm not sure if students who worked on this knew that it was a surprise for everyone. But and it turns out, yes, indeed, when we have the intensity of the light, which is not plane wave, unfortunately, which is we usually assume in the theory, your beams start to develop in the different modes. And Nick Lanning is the one who developed this, and he said it's a magic number of 5 modes which we need to include. And these are Laguerre-Gauss mode, which are nicely in circular. And the higher is the temperature, the more modes you have. So that means that the farther you go along, the worse things become because the modes start fighting with each other. So in fact, the big promising thing about that was that, well, as you increase the number of atoms interacting, you have more and more squeezing. But this squeezing now appears in the different modes, and they start fighting with each other. And as every fighting is not great, so at the end you end up with much less of squeezing you are getting. So that was a big takeaway of this project. And of course there were more work. And I'm mostly showing the experimental result, maybe a little bit as a kind of advertisement. If everybody interested in more details, I'll be happy to give them. So. I know I enjoyed our collaboration a lot. John said he enjoyed our collaboration a lot, so I'll choose to believe him. And these are actually very special pictures. That was the trip which we took in 2017 by invitation of of OIST Quantum Group, and that was actually the last time when I personally saw John. After that, we interacted a lot, but all basically by Zoom. And Elsa, John made fun of me because this is him presenting our experimental result. So he said, "That's the picture you chose to take of me," but it was, of course, not accidental that I chose this picture. It still tickles me to know that the great John Dowling was actually showing our experimental results. Okay, but we were able to continue. Now, as I said, the big promise of our previous results was that the squeezing is multimode, so we have this various information hidden inside. So we wanted to see how we can use it. And one of them, maybe we're able to somehow disentangle this mode and take advantage of the nice squeezing we're getting. Or maybe we can use it and finally take in images using the quantum noise. And again, this is the second generation of our collaboration. A lot of people have changed, and of course, John did. It still continues, but of course, without John now, but with his spirit. And the interesting thing that with everything is going on, turns out that this conference is the first time I meet a lot of LSU part in person for the first time, which is kind of crazy. Maybe at least the Juan, because I knew Juan for a very, very long time. All right, so to really make the story short, what we were trying, so I can tell you that when we start trying to image the quantum field, turns out it's a complicated process. And John had a lot of fun talking to experimentalists who didn't quite know what they're doing. But him making fun of us really helped because, of course, he saw a lot of things which were wrong and pointed out to us. And after you stop laughing, you really understand that this is great. So what we end up talking about is that how we can possibly take images with a very few photons, because that's a nice thing about the squeezed vacuum light, is that you don't have a lot of photons in these quantum states. So we were trying to see if we can take advantage of the fact that we can control the noise of these very few photons and measure them very well. So ultimately, after many variations, we identified the applications of basically fighting the dark noise of the camera. Because if we have a lot of photons, of course, we can always take it, and even though the dark noise of the camera exists all the time, it's much lower than the light we expose it to. However, if we have only a few photons, that becomes a real issue. So the idea was now to take all we know about measuring the squeezing and basically translate it into using the camera to take advantage of that. And of course, in the measurements which I showed before, we measured the squeezing using the homodyne detection. I don't think I need to explain what it is to everyone, but just in case. So we have our squeeze light, again, that one that has a very few photons, and then we mixed it with a strong classical light, and that one, and the difference between the two, the interference between the two, that's what we're actually detecting looking at the noise. So this way, we stay away from any other technical noises from the detector or the laser and everything else. So now, how we can use it for the camera? Well, we use the same trick, but now with the camera. So we actually investigated the two things. One of them is how you can take the squeeze light and mix it with a small amount of coherent light, and then just look at the noise properties on the camera, so the statistics of the photon counts on the camera, to get information about squeeze light. Again, the backstory is that we were very concerned experimentally that if you have leakage, and experimentalists know you cannot ever completely destroy the optical field. It's always will find its way to the camera. So we were not sure how it works. So again, this is the magic of John, who started with something which we thought a really big problem, but end up as a PRL paper. So Alicia was the main driving force in this with the work. So I'm not really gonna talk about this one, but the idea is again that by looking at how the count on the different camera spots, depending on intensity, change, you can extract information about the squeezing parameter of the state. This is a great method. However, it's more sensitive to the technical noises of the laser, so we didn't test it experimentally. Instead, we basically use the camera-based homodyne detector, in which case we take, again, the squeeze light, we mixed it with the classical light, and then we looked at the difference between the two camera images. So this is basically how it works. So this is the idea of what we call shadow imaging, because essentially you take the squeeze light, which again, it's a squeezed vacuum light, which has very few photons, but modified the quantum noise, and then you can put the object in it, and then whatever comes out, you can mix it with the local oscillator, and you can send it to the camera. It's, again, you have two images, and then you subtract them, and you repeat it many times, and this way you can take the variance in each pixel and look at the noise on the camera to get your images. And of course, because if it's a classical light, you wouldn't get any new information. However, if you have a quantum light, then if you have the squeezing and you look at this normalized variance, it will be less than 1. If you have the anti-squeezing, so extra noisy quadrature, then you will have higher than 1. And this is essentially how now you can get the information about the light. So I'm just showing one of the examples. So for example, this is the image of the target which we put in the beam. This is a cross. And then by looking at the normalized variance, and again, I'm not talking about this, you actually have to kind of look at the several pixels at the same time to get a nice image. You actually can figure out, can image the shape of here pretty well. We're looking at the anti-squeezed quadrature here, so it's an extra noise where we don't have a cross, and it's basically the variance drop to 1 when we do. Now, the really interesting thing here is that this method also has to have, seems to have much less sensitivity to the overall intensity on the beam, as long as we have the local oscillator there. Because if you look at the overexposed picture of the same cross, you may notice that we didn't have a single cross printed on this image. We actually have a multiple of them. So there is a kind of very small residues of the other crosses here. And in this image, you can see them. Whereas on the even like the normal image, you basically can't. So that was very exciting. Now, the next part, which we started, and that's unfortunately started after John passing, is we start thinking, can we use this method maybe for a broader range? Because the nice thing about squeezing is that it's a really fun quantum state which you can control a lot of things. However, the negative thing is that it's not really to get it. So for example, if you want to have some applications where things are really accessible, maybe squeezing source is not necessarily a very available resource. So the next question was, can we use the method if we use a more classical field? So for example, if you have a thermal vacuum, and turns out that basically it's the same thing, because the idea is that if you have your thermal vacuum, you send it through your system. Where it is blocked, it has it's converted into the regular vacuum, so your variance will be 1. If it's not blocked, then of course you will be able to measure it, and you can use the same trick of mixing it with a local oscillator to get rid of any effect of the dark noise or maybe background illuminations, which is also not great. And again, just to show one side, we were able to realize it with the vacuum. We kind of tried 2 things. One is a very well done, very well characterized vacuum produced by the Fourier mixing source, because we had it. But also we tried it with basically the rotating ground glass, where it can really be used by any laser light. And we were able to image with a pretty good precision. Another advantage of using a thermal light is then basically you can control your contrast of your noise change by changing how many photons you send in. So just by attenuating the field, we can make it either more robust or not, and we will be able to do it. Now, we were not able to do the resolution, but I think you can see that I think that it's about 1 centimeter scan on this images. So that's very exciting. Now the darker side of that is that in this work we went to another shadow, and that's the shadow between the classical and the quantum world. So now we are in a deep discussion with some of the referees on, is it quantum, is it classical, is it fair to call it quantum? And in fact, I think for the purposes of all our published work, it's not a quantum shadow imaging, it's a quadrature shadow imaging, because we don't want to confuse people and claim that it's a quantum imaging. So anyway, that's really the moment when I really miss John and his insight of this. And just to complete, it looks like I'm maybe a little too fast, but what we are trying to do now is to try to see if we don't even have to use the camera, or maybe we can take the advantage of using some of the structured imaging techniques, where instead of sending the local oscillator, which is just a coherent state, we can add some masks on it. And in this case, we can detect the noise variation with different masks, and we can see how much anti-squeezing and squeezing we have. And in this case, we will be able to assign the weights on this, depending on how well the mask of the local oscillator overlaps with the squeezed vacuum source after it's interacted with our target. And we will be able to reconstruct it this way. So this is very much work in progress. But again, very preliminary, asterisks, it may change. If, for example, we put a cross in our laser beam, we actually able to kind of reconstruct it using either classical interference of the local oscillator in the sum of the leakage of the coherent field, or we can also use the amount of anti-squeezing and look how much of it we have for different masks, and we can basically reconstruct the same cross. What is potentially even more interesting is that all the previous method relies clearly just on the looking at the intensity shadow. However, in this method, we can also trace the change of the phase as we change the different masks. And that also means that we might be able to reconstruct the phase using this way. So, for example, if we have the mask here, which has 3 different phases in this, by tracking the change of phase in the overall noise detection after different Hadamard mask edit, we actually might be able to reconstruct the phase landscape of this system. Okay, so yeah, I really wanted to have something like really nice and profound to say at the end. At the end, I just like kind of try to remember what really reminded me of John. And definitely, I know it's silly, but if you ever heard John saying Bogolubov, you will never forget that. And you will never be able to read this word without hearing his voice in your head. Article naming protocols, I don't know how many people know it, but this was genius. It works much better when John is around, but it still works. Ask me if you want to know that. People from the first generation of our collaboration know how many hours we spent discussing the optimal color schemes for our graphs. And I wish I wrote down all the colorful epithets John gave to various color scheme Mathematica offered. But now I pay much more attention to that. As I said, we worked on a lot of different proposals and a lot of different teams and so on. And few were funded and were very successful. A lot more were not. But pretty much in any case, John would just like make fun of it and laugh about it and say, okay, let's move on. And I think that was one of the best lessons I learned from him. And along the same lines is that he always believed in what he's doing, and he always believed what I'm doing, which was much more surprising to me. And I guess, yeah, just that's probably the main lesson, is that whatever you do, whatever you like to do, just keep going and things get better. And again, that's probably very, very silly, but by looking at the pictures from various events, I just found this one completely random clip, and I don't know, I listened for this like 10 times yesterday. So.
I hope you're not recording. I was trying to do that. It ends up on YouTube.
I just wanted to hear his laugh. Thank you.
Thanks very much.
So, Bogolubov in Russian means God loves us, or something like that.
God loving.
And laughter, God loves laughter. That's Dowling.
Yeah.
Can we go to view graph 19?
Yes.
So, I've always thought this business of imaging with squeezed light was great mathematically, but physically not so clear. Can I try it this way? If I have photons which are uniformly spaced, here, 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 then I know when a photon should be coming in. And if it doesn't, there's an obstacle. Is that the way you think about it?
Yes, I think so. So in a squeezed vacuum, it's a little trickier because then you have to include what is coherent vacuum. So there are some photons which are kind of intruders randomly coming. So I think it's pretty much the right story. So if the photons coming in at a regular point, then that's the variation we see. If you remove those photons, then we'll start noticing these intruders which come on a random time, and that's the kind of coherent state
So
photon
for
statistics.
entangled light, it's clear, but thermal light, not so clear.
So in thermal light, so it doesn't have to come orderly. It can be actually more random than the intruders. So if they come in the bigger bunches, which rarely happens with the coherent vacuum, you can still determine what's going on. But as I said, that's where we venture in a very shady territory.
Yeah, I thank you for the talk. Could you go to slide number 26, please? Because I really love the images that you're showing.
Yes.
And I think it's quite amazing that it works. It's basically echoing Marlon. I do have a question though. when I look at the classical input and the squeezed input,
Yes.
they look very similar. And in some sense, it doesn't really matter because you're doing imaging, so you want to have the actual image, that's the pudding that we're eating. But as a theorist, I also want a number, how well they're doing. So do you have a figure of merit that you can compare the two systems?
We will when we're ready to publish.
Okay. Fair enough.
So at the moment, in fact, full disclosure, in case, so in the previous work, for example, when we used the thermal light and the squeeze light, fundamentally there was no real advantages of using either of the noisy fields if you have a perfect camera. But luckily for experimentalists, we never do have a perfect cameras. So the noise measurements were really helping us to, and using the homodynamic detection really helped us to negate the effect of the dark noise of the camera without increasing the number of photons which we send to the object. And this is where coherent, we cannot do anything with the coherent light like this way because the difference between the noise in vacuum and the coherent field is non-existent. So here again, at the moment it's a little more of, we're really trying to fine-tune our method. So at the real difference between the classical and the squeezing is that for the classical we actually send in much more photons to get this image. So it is not, again, it's not a kind of apple-to-apple comparison. It's not going to be as good if we send the same kind of, well, again, it's the minimum of photons we can have is like a leakage we have. So this is a little more for the demonstrations and for us, but it's probably, I suspect it will be similar to that, where it might not be fundamentally better than using the coherent light, but it will find the actual problems which people can face. Yes.
Wonderful talk. So if I'm understanding it, you're getting the difference between the Poissonian distribution of the vacuum and either the thermal light super Poissonian or the squeeze light sub Poissonian. But you can often get stronger anti-squeezing than you can squeezing. Would you get better performance than using the anti-squeeze quadrature?
Most of it is actually using anti-squeeze.
Okay.
Yes.
Yeah, beautiful talk. So since you're talking about using thermal states, I'm wondering what the potential applications to something like astronomy could be, where you have thermal states coming from stars. But I'm wondering if the main limitation is that you need to have, the bandwidth needs to be narrow enough that your detectors are fast enough that they can sort of, they're in the short time regime. Like if you wanted to see a G2 measurement, you need to have very, very fast detectors.
Yeah, so it's actually an excellent point. That's something we need to think about. So I'm not sure, so the one of the advantages of using it for, like we had in mind more like biological applications. So because we're still using the local oscillator, and I'm not sure it will be easy to, like, of course if it's a narrow band, we will be able to kind of grab the local oscillator and do it still. But it's, I'll need to think about it. If it will be able to really help with applications where the kind of the light sources come from some light sources outside and not available, and if we can enhance that using a similar approach.
All right, great questions, but thank you
you.
again.